Okay, thank you. So first I would like to thank the organizers for giving me this opportunity to talk about some recent work. So I will talk about FRB modeling, and well, from the background you can guess what's my favorite kind of source for FRBs. I guess otherwise I wouldn't be here anyway. And more particularly I will talk about magnetospheres. Okay, so just a quick slide about FRBs themselves. So they are, well, very short in time, intense radio bursts. They mainly come in two categories. One is the one-off events, where basically you see one event, possibly with 2 or 3 components, and then you don't see it anymore at all, at least so far. And their main characteristic, one of the main characteristics is to be broadband. And if there are 2 components like this, they may go up in frequency or down in frequency, either way. So this is chain data from the Galactic Magnetar SGR 1935. So that's the only FRB that we know from the galaxy. I mean, okay, like we may discuss a little bit if it's really an FRB or not, because it's less intense than the extragalactic ones. But it does look like other one-off events, and the advantage is that we actually know the source. Now there are repeaters, which are FRBs for which we see sometimes many events, like for this one, 121102. And their main characteristics is that they are typically narrowband, and when they have several subcomponents like this, it will always go downward drifting with frequency. So that's an important characteristic. So then the spoiler slide, if I may say. It says several things, but essentially the idea is to try to have the most generic possible model in order to be able to, and the simplest one as well, in order to be able to produce actual observables in terms of dynamic spectra, to hopefully be able to fit it to the data. And this depends on like general characteristics of the magnetar, such as its spin period and its magnetic geometry. So then basically you would have to fit together all the events that you have for a given repeater, so it's a lot more interesting for repeaters. So you have to fit them simultaneously because they all share these properties, right? So instead of fitting them one by one, as it's often done. The main message here is that the burst morphology of the events in the dynamic spectrum encodes this kind of information, at least according to the model. Okay, so what about the model? So it relies on like a set of a few hypotheses. Mostly that the emission, the blob of matter responsible for the emission is very localized in time and space. So that's motivated by the idea that, okay, it's very short emission and it's also narrowband for repeaters. So both of this translates in a very small emission region. The plasma is propagating relativistically, so then the emission is very beamed. We assume that the source is in a rotating frame, okay, and to link geometry to frequency, we assume radius to frequency mapping. So basically, the further the blob is from the star, the lower the emitting frequency. That's essentially what it says. And you can do the same thing with polarization using the rotating vector model. So then what it does is that if you have a blob of emitting matter, it's propagating along streamlines. Typically we propagate along several streamlines. So just to make things even simpler, we just take like the median streamline if you want. So we only have one streamline, and then we encode the divergence of the streamlines, like their opening angle if you want, into an effective emission angle. So that's one parameter of the model, eventually. So that's to make things simple, and then what you find is essentially that the emission properties depend only on the local geometrical properties of the streamline, that is its tangent direction as well as its curvature and plane of curvature. All of this is in a rotating frame. Okay, so what you get from that, the basic thing that you get from that is an envelope in the dynamic spectrum. Why? Because as the blob of matter propagates along the line of sight, well, you see different frequencies because you have a difference in altitude, reduced to frequency mapping. But also, like, so you have a cone of emission, and then you can see the bursts only they're emitted while the line of sight of the observer is within the cone of emission, right? And then as it goes along the line of sight, at the beginning, up, you don't see it at all. Then starting here, you start to see the line of sight, including there. And then it's turning, and then at the end, you're at the end of the cone, you don't see it anymore. So in the dynamic spectrum, this translates in something like this. So it's just a drawing, right? But just to give you the idea. So outside of this, you are not able to see it. Then if you have a favorite emission model, you can plug it in, and you will be able to generate bursts like this. So in the following, that's what I will do with a very simple model that I don't have time to describe, but it's not extremely important for what I have to say. And also I will assume that it's not actually a cone of emission like a sharp cone, it's like more like a smooth angular profile of emission like a Gaussian shape. So then the burst can bleed out of the envelope, like the envelope is more like a contour of constant emission angle. Okay, so once we've said that, we need to assume some general geometry for the streamlines. And here I would just assume that the streamlines are nothing else than the field lines of a dipolar magnetic field, right? So, well, I mean, that can be motivated by what we see in pulsars, but also it's just simple to calculate. I assume that the spin period is 3.2 seconds. It's not random. It's the spin period of the galactic magnetar. Thank you. So that's the spin period of the galactic magnetar, so the only one for which we know actually the spin period, so that's interesting. And here I show a collection of envelopes generated by the model at a radius of 100 stellar radii. And they are taken in the vicinity of the polar cap field lines. And well, one important property is that they are all wideband. So you cannot see the scales here, but they are all wideband. And they can go either up or down in frequency, right? So then, well, just to try to play, this is not an actual fit, it's just me fiddling with the parameters a little bit by hand. You can try to pick up one envelope that looks good. So actually, I think it's this one. Then you zoom enough to have the right frequency band. And then you add two bursts in shades of gray here, using some emission model. And you see that you can obtain something that looks very similar to the event recorded by Chime from the galactic magnetar. So that shows that it's not absolutely ridiculous. But again, it's not an actual fit. So then how to reproduce repeaters, which I said are downward drifting in frequency and they are narrowband. The simplest way I found to do that is to actually add a strong toroidal component to the magnetic field. And also to speed up a little bit the spin period. But don't take this too literally, it's actually degenerate with other parameters, it's just like parameters I used just to make an example. So the important thing with this is that the toroidal component allows to generically reproduce downward drifting subpulses, I mean downward drifting envelopes, and narrowband emission, like the envelopes are narrowband, and like whatever the line of sight. So that's actually kind of interesting. In this case, the frequency drift is comparable to what we see from some repeaters, and the toroidal field at the place of emission in the magnetosphere is about half of the dipole strength. So why am I speaking about toroidal fields? Well, there are some motivations for that, where the main thing is that for magnetars, we expect that inside the star there will be a very strong toroidal fields that are generated by dynamos during, so this is a simulation for proto-neutron stars, where you can see like the toroidal magnetic field lines inside, which are like hundreds of times stronger than the dipole inside the star. Now the question is, does it bleed out? So if, like, often like the boundary conditions are such that it's vacuum outside, and so therefore nothing goes out because it's shielded by infinite conductivity at the surface, then usually it's not vacuum outside, right? There's a matter. Well, infinite connectivity may be questioned as well. In any case, there is this simulation, it's very recent work, which is very nice because they actually solve consistently both the inside and the outside. And then they see that they have toroidal field that's color-coded here that goes outside, and it's typically like 10 times or like maybe 4 times. I don't actually exactly remember, but several times the dipole field outside. So then this is some preliminary fit to one event of the chain FRB data for a repeater. Again, you have to fit all the events at the same time, but then there will be too many plots. And so you see like the result of this preliminary fit. It's not perfect, but it's not completely ridiculous either. So this is like the data of the residuals. So that's what we get at the moment. And then I can run Monte Carlo for this, which again, it's very preliminary. I actually don't myself trust the numbers yet, but it's just to give you a feeling of the kind of thing we can expect from studying the morphology of the bursts. So ideally, that will be the end product. And what you get is like, so for the same repeater I showed just before, in this case, it was spin period about 2 seconds, very strong toroidal field at the surface that decays as 1 over R4. That's basically the kind of result we can get. Again, don't remember too much these numbers because it may change. This is very preliminary. So now that, well, the last message is okay, burst morphology may encode a lot of interesting things. The preliminary results that I show, you can convince yourself of a nice story, which would be repeaters are high toroidal field magnetars with toroidal field which really goes out of the star. Therefore, they are very active because, as we know, the toroidal field, I mean, the decay of the magnetic field in magnetars is what creates the bursts. Well, they are somewhat younger, meaning they didn't dissipate the toroidal field yet too much. And then the one-off events, they would be like lower toroidal field to the point that actually dipole geometry actually works. And therefore, they are less active, and in this sense, they are older. So that's it. Thank you.
Thank you a lot. So it's time for questions. It's quite hard to time, but you can do first.
So first question is, so this is actually not generated by the model. This is arbitrary, so you just feed parameters for this. Like basically you have a burst whenever you have a burst, the magnetar decides. That's as far as the model goes. So you have to, you put them ad hoc, right? You say, okay, I want a burst here, a burst here, a burst here, and you say how long you want it to last. And then that translates, in the model that translates of how big a blob of matter you have. At what time? And then it's ejected by some event from the magnetar. Okay, that would be like the general idea. But this is like parameters you fit, basically. So it makes a lot of parameters at the end, but it's actually less parameters than if you had to fit all of the components individually with Gaussians, the way it's done in some papers, for example. Second question, the emission mechanism is actually assuming so, I mean, the frequency is set by radius to frequency mapping, right? And then it's just assuming that the matter that's emitting is follows a Gaussian profile along the streamline. And then that translates in something that actually looks a little bit Gaussian, but is deformed. So, I mean, the motivation for that is the observation that in works that we're trying to empirically fit Gaussians to bursts, it was actually working reasonably well. So, you know, then if you have like a slightly Gaussian, deformed Gaussian, maybe it will work better or similar.
Okay, so it's like black box.
Sorry?
It's like black box that converts.
Yeah, I mean, this is empirical. This remains empirical, yeah. But the thing is that it's constrained by the geometry. We can't do anything.
Since we run out of time, I think we should end the talk here. Sorry, but if you have any questions, you can scan the QR code.